All right, so welcome everyone to the Shannon channel. I'm really happy this Friday to have Babak Hassibi from Caltech give a talk. And today's talk has a very interesting title. It's called The Blind Men and the Elephant, The Mysteries of Deep Learning. Thanks, Babak. We're all listening.
Yeah, thank you, Salim, for the kind introduction. And thank you, all of you who are here. This is a wonderful opportunity for me, and I think Salim has been doing a wonderful service to the community with these lectures. So I'm, maybe a little uncomfortably going to talk about deep learning today, and I'll kind of allude to why. So deep learning is something that I'm sure everyone has, it's even in the popular press, people talk about these things. And so it's had a huge impact in machine learning and AI, and has made its way into all kinds of different applications. It's revolutionized computer vision and image understanding, speech recognition, but we still don't really understand why. And so that's part of the reason for this title. I'll make an analogy to the famous story. But so let me get into it. And as I mentioned, I'll be going between presentations, and hopefully I can do that smoothly. Okay. So as I said, undeniably deep learning has enjoyed a great deal of success. There's many applications, that it has really enabled and improved and so on. So I'm old enough, to kind of remember, when neural networks were also popular in the 80s and 90s. So I was a grad student in the 90s. And so when I first saw deep networks, I was kind of surprised because superficially, at least to me, it seemed that there was not a whole lot of new innovations compared to what had been done in the 90s. Already in the 90s, there were theorems saying, so if you look at what I've shown here, so I have two networks. So there's a 3-layer network on the left, which is kind of what people did in the 80s and 90s, and already then they had theorems saying that a network with this structure was already a universal approximator of functions and so on, so that there was no need to go to more layers. And so deep networks really have many, many more layers. And so to me, it was okay, so is that all that there is? The algorithms used for training, people use these gradient descent methods, SGD, and their variants were what were being used back in the 80s and 90s too. They were called backpropagation back then. So to me, it was a bit baffling as to why these were working, because I didn't see a whole lot of new ideas. And maybe that's, being a bit facetious in what I'm saying, but I think there's some truth to that. Okay, and so you might ask the question, why is it that deep networks have has this huge success? And you might say, well, maybe it's the network architecture, because we have many layers as opposed to just the 2 layers or 3 layers, depending on whether you count the weights or the neurons, if you will. You might say, well, typically deep networks are convolutional. They're highly over-parametrized, and I will speak to this extensively today, meaning that they're way more weights than the size of the data set, so they are over-parametrized. And then there's differences in the nonlinearities. In the 80s, 90s, people use sigmoids. Now they use ReLU, which are kind of like these diode-like responsive nonlinearities. One could argue that, maybe the success is that now compared to 20 years ago, we have much more data. We're in the era of big data. We have much more computational power. And so it's really just that we can now train these things much longer over much larger data sets than we were able to in the past. Others might argue that, maybe there's some magic with the algorithms. And to me, that's a little strange because, as I mentioned, the algorithms haven't really changed a whole lot since the 80s and 90s. And if anything, I would say the algorithms have even been dumbed down because the data sets are so large and the dimension of the problems, so big that, any fancy algorithm is not really scalable. And so that's kind of the predicament you're in. And so the picture I have here is, when you look at these different aspects, trying to understand what deep learning is, the analogy is the parable of the blind man and the elephant, where everyone looks at a particular aspect and draws some conclusion. And I think the as with the parable, you really need a holistic view of deep learning to try to understand what's going on. And we're not there at all, I would say. And so, I don't know why I'm not going to the next. Oh, there we go. So again, not to be facetious, but I will say this as well. And so if you think about this at some level, you know, especially given the fact that these deep networks are highly over-parametrized, the correct question might not be, you know, why does deep networking work? But the correct question might be, you know, why does deep networking or deep learning, why does it not work, right? Because you would think that it shouldn't work, right? So again, back in the 90s, you know, I was always told of things like Occam's razor and the curse of dimensionality, and that you don't want to overfit. And so the figure I have on the bottom left, which is, you know, polynomial fitting. So you have some number of data points that you want to fit, and if you perfectly fit them, if you interpolate the data, you get the red curve. Say that's the 9th degree polynomial, I guess, because we have 10 points. Whereas, you know, what you actually want to do is to fit it with a, you know, a 3rd degree polynomial here, which is the green curve, and it generalizes much better, as you can see, because the red curve has these peaks and wiggles, which is not reflective of the true data. So that was kind of the convention, saying that the whole, you know, premise in conventional learning was not to overfit. And so when you look at deep networks, what happens is that you not only are overfitting to a comical extreme. You have orders of magnitude more parameters than you have data points. And I'll show you examples. So typically you'll have thousands, tens of thousands of data points, whereas the number of parameters in your network that you're training for is in the millions or tens of millions. So it's orders of magnitude more. And so you would think that, you know, you should overfit and not generalize, but what people see with these deep networks is that they do generalize. And in fact, there's been multiple studies, and so this is now referred to something called the double descent phenomena, which shows that, in fact, you know, with these deep networks, the more parameters you add to them, the better they generalize. Okay, and so this is kind of baffling, and, you know, you might ask, you know, what is it that's going on, and why it is that that this is happening. And so that's what I kind of want to address a little bit in this talk. And, you know, I'm going to do it through the vantage point of the training algorithms that are being used. And so this was the colorful part of my presentation. I'll come back to this, these slides a bit later, but now let me go to the maybe more technical part. Okay, so as I said, you know, so my focus is going to be in this talk on trying to understand what the algorithms in deep learning are doing. And these algorithms, by and large, are stochastic descent methods, and so I'm going to start talking about them. Okay, so let's just set up the setting. I'm sure everyone is familiar with this. I'm going to look at supervised learning, which is what deep learning typically is about. So we have a collection of data points. So we have inputs X, you know, these are sometimes called the feature vectors or the regressor vectors, and we have labels Y, or outputs, which are scalars typically. And in this context, the notation I'm using is that there's T such data points, T for the training set, and say my input vectors are little n dimensional. I'm going to assume that this pair is related through some parametric model, so that my labels are obtained by applying my input vectors to this parametric model. The parameter vector here is W. It's a capital N dimensional unknown weight vector. But there's some W that generates my data. And I'm also here including the possibility of maybe some noise, or maybe, you know, this parametric model is not powerful enough to, you know, fully capture the relationship between Y and X. And so whatever modeling error I have, I put in this V. So I potentially could have some term V here, which might be modeling errors. It might be noise. It could be a combination of the two. Okay, so this is kind of the setting. So there's some true W that is generating, my labels when I get my feature vectors, okay? And so in supervised learning, we're essentially trying to learn this parameter W with the goal that if I'm given feature vectors outside this data set, but drawn from the same model, I do a good job of predicting what the corresponding labels are. And so the way this is done, as I'm sure you know, is by, and here I've used the word ostensibly, by minimizing some loss function, what I'll call a global loss function. It's a function of this weight vector. And it's the sum over your data points, your training data set, of these little l's, which are local loss functions, which measure the distance between, or the difference, or, between the labels and what the model predicts to be, okay? And so these local loss functions I'll call L sub I referring to the data point that they're being computed at. So the global one is just the sum of these loss functions over all the data points. Li signifies just one of them, okay? So I'll make a few assumptions. The little l here I'll take to be differentiable. It's 0 if and only if the two arguments match. And so often we will take L just to be a function of the difference of these two things. And in that case, L is convex and has a global minimum at 0. So this is often what I'll take, but it doesn't have to be. And so the classical example is quadratic loss, where the loss is just the square of the difference between the label and the output of the model, okay? And so gradient descent, just quickly now, it's a method of trying to estimate the weight vector where you just update along the negative direction of the gradient of your loss function. Eta is a learning rate or step size. It's a positive quantity. It tells you how quickly you go along the direction of the gradient. I'll say a few words about this. So gradient descent goes back, it has a long history. It goes back to Cauchy. I'm sure, this just looks like some guy from the 19th century, but this is Cauchy. And so there's an interesting story there, so I will tell you about this. So he invented gradient descent in 1847. And so when I look at these dates, I am very encouraged because it tells me that Cauchy did this when he was 58 years old. And so that means there's still hope for me. But anyway. So basically what he was looking at trying to solve a system of nonlinear equations, simultaneous equations, in some astronomy application. And the way he did that was he took each equation, set it to 0, squared them up, and tried to minimize that sum of squares, hoping that if he hit a global minimum that, he would have solved the equation, okay? And so he realized that, when he was doing gradient descent, that, it may or may not converge, convergence depends on the size of this, this learning rate and all. He was aware of all of this. And Cauchy is well known. He was probably considered the most rigorous mathematician in the 19th century. And so he was very displeased with this fact that, you may or may not get convergence. It depends on eta and all these kind of things. So he's very apologetic. So at the beginning of the paper, he says, I'll restrict myself here to outlining the principles underlying my method with the intention to come again over the same subject in a paper to follow, because he wanted to actually prove something about this method. And so there is no following paper. Which I think signifies that the problem was not as easy as Cauchy had thought it would be. But this kind of illustrates that Cauchy was well aware when he invented this method of the issues and the shortcomings. And so what is well known with gradient descent is that if the step size is small enough, you converge to a local minimum of the loss function here. Now, I should, emphasize that even though these loss functions are, convex in their argument, once you introduce this f, if f is some highly nonlinear function, which it is in the deep networking convex, capital L overall is highly non-convex. And so, there's a difference between local minima and global minima in general. Now, when you have lots of data points, computing this full gradient can be cumbersome, and so people often use what's called stochastic gradient descent. This was invented by Robbins and Monroe in the early 50s and then rediscovered multiple times by different authors. And so there's variants of this. I won't go through that, but the simplest variant is where rather than you compute the entire gradient, you update your weight vector every time you use a data point. So this L sub I, if you recall, was the loss function for the ith data point. And so in stochastic gradient descent, this is what you do. You don't sum over all the loss functions for every data point before you compute the gradient. You kind of do what's called sometimes the instantaneous gradient. You compute the gradient for each loss function. And the reason why this is called stochastic gradient descent is because it's an approximation to the true gradient. Its expected value gives you the true gradient. And so you can either cycle through things periodically, in which case it's not really stochastic, or you can draw the data points at random, in which case it is. But either method you use, this is referred to as stochastic gradient descent. So the S is for stochastic. Has some advantages. So SGD, can potentially escape local minima. The reason being is you're not really going along the direction of the true gradient. It's a different direction, and so you might be able to escape local minima. And so the question is, does SGD converge? And so if you think about it, not really, because even if you're sitting at the global optimum, where the true gradient is 0, these instantaneous gradients may not be 0. And so even if you're sitting at the optimum, you'll be jiggling around. So SGD generally, if you have a fixed step size, does not converge, okay? The only situation where it converges, if for a fixed step size, if there is a weight vector, W here, that simultaneously minimizes all these loss functions. Because if there is a weight vector that simultaneously minimizes the loss function for every data point, then at that W, all of these gradients vanish. Because this W is a simultaneous minimizer of all of them. And what that means is that there should be a W where for everything in the data point, the output of the model matches the label. Okay, and that means you should be able to perfectly interpolate the data. Okay, so that's the only situation. So if there's a weight vector that perfectly interpolates your data, SGD converges. Otherwise, there's no way it can. Now, often what people do to get convergence with SGD is they, pick a step size that goes to 0 to get convergence, which is fine. But to me, again, this sounds a little bit silly because of course, if this step size goes to 0, you will get convergence, but you'll get convergence not because of anything inherent in what's going on. You're really getting convergence just because after a while you're not updating anymore. These update coefficients get smaller and smaller. So it's kind of an artificial way of getting convergence. Okay, so anyway. So that's a little bit about SGD, and so I want to focus a little bit more on what it is that SGD does. And in order to answer this question, I'm going to look at a simple case where the model is linear and the loss is quadratic. Okay, and so if you think about SGD, so when the model is so this is kind of another way you can represent it. So I wrote it as a recursion like this. But if you think of what it does, at every time instant, it really does the following optimization. It finds the optimal W that's close in this 2-norm sense to my previous estimate. But, I also want to minimize its alignment with the gradient, the instantaneous gradient at the previous thing. So if you actually go ahead and solve this problem, which is easy to do by differentiation, you will get the SGD update. So this is what it does locally, okay? Which is fine, but it's not all that insightful. And so you might ask, what is it that stochastic gradient descent does globally, over the course of the training? And to answer that, as I said, I'm going to look at the linear model. So what that means is that, you know, the function is just a linear combination of the input, and that linear combination is given by this weight. This is, again, potentially either the measurement noise or the modeling error, and I'm going to focus on quadratic loss. Okay, and so SGD has an explicit form now, and in order to understand what's going on, I'm going to look at the following, you know, min-max problem. And so let me describe what this is, okay? So it has a denominator and a numerator. When I look at the denominator, so the denominator is kind of all my uncertainties, right? So I start off SGD with an initial guess, which I'm calling W naught. And so this first term is my kind of uncertainty, if you will, between the true W, which I don't know, and, you know, what my guess is. And these terms here, and I'm measuring this uncertainty like in a 2-norm squared, these are all the uncertainties coming from, you know, either my modeling error or the noise. So that's what I have there. So the denominator is kind of like the energy of my uncertainties. What I have in the numerator is the uncertainty kind of after, you know, I've done m steps of the algorithm. So I think of m as being the horizon of running the algorithm. So after m steps, I have the new estimate W of m. And this is my uncertainty of the true W after m steps of the algorithm. But I've added to it this term here, which is what I will call a prediction error. It's the difference between the, you know, uncorrupted, if you will, output of the true model for the true W compared to what I predict the output would have been when I have observations, or, you know, I've run the algorithm up to time I minus 1. Okay, so this is kind of like a prediction error. So that's what I'm putting up here, and I'm going to look at kind of a worst case thing. So I'm going to allow, you know, nature or the opponent to choose W as it wishes, you know, to choose these disturbances as it wishes, to maximize this, because I will do a bad job in estimating W if this ratio is big. So if I have a little bit of uncertainty, but this ratio is big, it means I'm doing a bad job in estimating. And so what I want to do is to choose the best algorithm, if you will, to minimize this maximum thing. So it's a min-max problem. And the remarkable thing about SGD, and this is a result that goes back to PhD work I did in the 90s, is that if the step size in SGD is small enough, then this min-max problem, well, actually I should have said this is not really a step size. I mean, it ends up being the step size in SGD, or the learning rate. It's really the parameter that weighed these two terms, both in the denominator and the numerator. If this is small enough, then this min-max is actually 1, and SGD is the optimal algorithm for this. So it actually solves this problem. This is what it's doing globally. It's minimizing the maximum, if you will, energy gain from your disturbances to your prediction errors and the final estimate. It's just a property that SGD has. It's really what it's solving, you know. So if this was what it's doing locally at every step, this is what it's doing globally. And so there's various interpretations for SGD that you can get from this. This kind of says the algorithm is robust and conservative. It's robust because it safeguards against the worst case. It's conservative for the same reason, because it's safeguarding against the worst case. There's also a stochastic interpretation that I can give for this, but I think in the interest of time, I will skip that. Okay, and you can extend this to time-varying step sizes. I kind of want to maybe give you a little bit of a hint of where the proof of this comes from, because I'll be using this when I go to deep learning. So I'm going to look at two error terms. So this is the prediction error that we saw earlier. It's the uncorrupted output at time I minus what we predict it to be. And I'm also going to call something the innovations, which is the difference between the actual label and what we predict it to be. So these two things are potentially not the same when Y has a noise term in it. And so what you can show SGD does is it satisfies a particular conservation law, which is the following thing. So the error you have at time I minus 1 plus the square of the noise breaks up into these three terms. It becomes the error at time I plus the prediction error squared plus a term involving the innovation. So this is being conserved at every point in the algorithm. Okay, and so I want to say something about this. So, so this is at every point in the algorithm. And so certainly if I start summing this up from time 1 to time n, I get a global conservation law because I get a telescopic sum. When I start adding these up, I'm left with W minus W0. I have a W minus WM on this side, but all the other WI terms cancel telescopically from both sides. And so basically this is what I get. This, recall, was the denominator that we had. This part here is the numerator with the prediction error, but there's an extra term. And so the whole point is that, when eta is small enough so that this is positive, I can lower bound this by the following expression by just dropping off the third term. And that, in fact, once I divide by this denominator, shows that the ratio is less than or equal to 1. Okay, and so I've already shown half the theorem that, SGD guarantees that this is less than or equal to 1. The rest of the theorem just constructs a worst case W and V to achieve 1, and then you're done, which I won't do. The thing I want to emphasize about this is that this thing here that I've written, it's a global conservation law. It says that over the trajectory of, the SGD algorithm, this quantity is preserved and it becomes this, okay? And so this is very akin to, those of you who know classical mechanics. This is kind of like a, Lagrangian picture where, you have particles moving in classical mechanics, and, at every instant the particle, you can think of it as either minimizing a Lagrangian, or you can have a Hamiltonian picture where you say, okay, particles move in such a way to conserve something. There's some conservation law. You conserve the Hamiltonian. And so this is kind of that picture here. This is like the conservation law that corresponds to this instantaneous optimization at every point. Okay. So what is this good for, and why did I go through all of this? And so let me maybe skip this and kind of show what this can be used for. So recall that, in deep learning, I emphasized a lot that the system is over-parametrized. And so we're in this interpolating regime. We have many more weights than we have data points. And so let's look at the implications for that in this very simple linear setting. Okay, so I'm going to assume that the dimension of my weight vector, which is n, little n, which is the dimension of my input, is bigger than the number of data points. Okay. So this is the setting. And so what this means, if I have more parameters than data points, it means that I can perfectly interpolate the data. There's a W that perfectly interpolates the data. I don't need this V term. Okay, and in particular, there's a whole solution space for little w, which I will call script capital W, which interpolates the data. Okay, so this is the definition. This is all weight vectors that interpolate the data. In fact, this generically will be an n minus capital T dimensional space. Okay, and so in this setting, if you write the conservation law, so as I said, there's no V, so this is the first term. And then when there's no V, the innovations and the prediction error are actually the same thing. And so when you write the conservation law, basically it boils down to this. And so if you stare at this thing, okay, and you let m go to infinity, so W minus W naught is fixed. It's some finite value. And so as m goes to infinity, this infinite sum should be finite as well. And so I'm hand waving here, but this can be made rigorous. So what that means is that these EIs, these errors, the innovations, have to go to 0. Because if they don't, then this term can go to infinity, because this coefficient here is positive if the step size is small enough. And so if the E's are going to 0, it means that, we are interpolating the data in the limit because we're perfectly matching every y. Okay, so I already demonstrated that SGD converges to something that interpolates the data. So the limit of the WIs for SGD is something I'll call W infinity, and it belongs to this interpolating set. Okay, so that's very easy. You can use this conservation law to very straightforwardly show convergence. Question is, what do we converge to? And again, if we look at this this conservation law now at infinity, so we converge to W infinity, and so this is the converse, the law that we have. And if you look at this term here, it's independent of W, right? It depends on Y, it depends on the run of the algorithm, so it depends on W naught, but it does not depend on this interpolating W. It's not a function of it, right? So the only way that we get a function of W here on the right-hand side is through this first term. And so what that means is that if I minimize this first term here over W's that interpolate the data, this term is independent of such W's. It means that, if I want to minimize this term over W's that interpolate the data, I have to minimize the first term on the right. But that's clear. The first term on the right is minimized when W is W infinity, because W infinity is in this set. It interpolates the data. And so this is the remarkable thing that we've shown. It shows that what SGD converges to, what W infinity is, it's something that interpolates the data, but that is as close as possible to W naught. So this is the picture. So what SGD does is you start off with an initial guess W naught. This is the space that interpolates the data. And what you converge to, what W infinity is the closest point to what interpolates the data. Okay.
Look, I have a quick question to make sure I'm getting. So this is in the regime of where you're over-parametrized, right?
Yes. Everything I'm talking about is over-parametrized. And I'm doing this with a goal. So, this is actually not very difficult to look at, but people who were studying SGD and these kind of things back in the 50s, 60s, 70s, whenever, never cared about this regime because they had no reason to look at a regime where you're over-parametrized, okay? Well, if you ever ask the question, what does it do when you're over-parametrized, this is easy to establish, and I just showed you a proof of it.
Okay.
But the reason why I'm doing this is because this is the setting for deep learning, and I want to get to that. So this is important to know. So SGD, with a fixed step size in the linear case, first of all, it converges to something that interpolates the data, and what it converges to is the point that is closest in Euclidean distance to what I initialized with, and that interpolates the data. So W infinity is basically the closest point in the interpolating set to where I start out. That's kind of the conclusion. And so this is called implicit regularization. You see, when we did SGD, so why I'm calling this implicit regularization is because it's choosing a particular solution, right? But this is done implicitly. When we wrote SGD, we had no intention of it solving this problem. It kind of came about, okay? And in particular, if you initialize with 0, which is typically what people do, then this term drops off. And so what this really says is that when you initialize SGD with 0, you find the interpolating solution that minimizes the 2 norm. So you get the minimum L2 norm solution, which is really what you get from the pseudo-inverse. So SGD kind of implements the pseudo-inverse in this case. But this is implicit regularization. So I've regularized the solution when I run SGD to the minimum 2 norm solution. Okay? So that's what I was saying. Other people have recently noticed this as well, so we're not the only people to have realized this. And a question you might ask is, okay, now that we see this regularizes, what about other regularizers? And so let me move to that. And to do this, I'm going to digress a little bit, and I'm going to introduce you to something called Bregman divergence. Some of you might have seen it. And so to introduce Bregman divergence, I'm going to start off with a strictly convex differentiable function psi. So we all know what convex and differentiable means. A strictly convex function means that So whenever you write down the definition of a convex function, there's an inequality. If that inequality is strict, the function is called strictly convex. And I'll speak about this a little bit more later. So we call this thing the potential function. And then the Bregman divergence is defined in the following way. So think of this curve here as being your differentiable potential. So it's a convex function. So a convex function has the property that if you look at it at any point w prime, say, and if I draw the tangent to the convex function, it lives below. So tangents are always below the function. That's a defining property of a convex function. And if it's strictly convex, it's strictly below. And so if I now take a look at the function at another point w, the difference between the function at w and this first order approximation, if you will always be non-negative. That's called the Bregman divergence. So the Bregman divergence for a potential is a function of two variables. The second one is where we draw the tangent. The first one is where we evaluate the potential. So it's a difference between the potential evaluated at w and the first order approximation of the potential when you expand it around w prime and then evaluate at w. So this is like the 0th and first order Taylor series expansion of this. And as I said, because this is a convex function, it's non-negative, because psi is a convex function. And so in other properties, so in the first parameter, because this is convex and this is linear, you're convex in the first argument. And furthermore, because we have strict convexity, the Bregman divergence is 0 if and only if the two arguments coincide. So at this point here, okay? So Bregman divergence is a nice thing because you give me any strictly convex potential, I can immediately generate something that looks like a distance metric because it's non-negative. And there's many examples of this. So if you take your potential as being the square 2 norm, then the Bregman divergence is just the square of the difference between the two arguments. You know, I guess this is a Shannon lecture, and so there should be entropy somewhere in a Shannon lecture. And so if you take your potential as the negative of the entropy, which is a convex function, the Bregman divergence reduces to the KL divergence that we all know of. So in fact, that's one reason why this is called a divergence, because it's a special case of Bregman divergence. Okay, so that's my digression. Now, for the purposes of this talk, the reason why Bregman divergences are useful is because they share many characteristics of quadratics. In some sense, you can think of Bregman divergence as being the generalization of the notion of a quadratic function, because when you look at what the Bregman divergence is, you start off with this convex function, you subtract the 0 and first order terms. What you're left with are quadratics and higher, okay? And so that's why, in some sense, it's like a generalization of a quadratic. And so it shares many characteristics, and I'll show you a few of these. So with quadratics from high school geometry or trigonometry or whatever, you've probably heard of the law of cosines. And so that's what it is. If I have 3 vectors, then I don't know, w minus w prime squared is, I think, this thing squared, whatever. I mean, this is what it is. There's this inner product here. So there's a similar thing with Bregman divergence, where instead of looking at the differences between these vectors, you look at their Bregman divergences, and this inner product changes a little bit. You end up with gradients of the potential, but this is a counterpart of the law of cosines. More importantly, there's a completion of squares type thing that you can do with Bregman divergence. So whenever you have quadratics, so I guess in high school, the first time they show you how to solve a quadratic equation, you complete squares. There is a completion of squares argument for Bregman divergence as well. So if you have 2 different Bregman divergences, both of which they're functions of w, you can kind of rearrange them in such a way that all the dependence on w just shows up in one term. So these are kind of constant terms. And this is useful because if you're trying to, say, minimize the sum of 2 Bregman divergences, once you do a completion of squares, you just need to minimize, say, this one term. You get all your unknowns into one term. Anyway, so there's, I mean, this is just a digression, okay? So the reason why I'm saying this is because this allows you to generalize SGD to something called stochastic mirror descent, where what you do now, if I'm trying to say, run this algorithm, you know, with SGD, recall what the algorithm was, is we minimized the half the squared Euclidean distance between W and the previous estimate, plus a term involving how aligned we were with the gradient. If you replace the 2 norm with a Bregman divergence, you get something called stochastic mirror descent. And again, there are theorems for this. If the learning rate here is you know, small enough, you can show that this algorithm will converge to a local minimum. There's a stochastic version of it as well, where you replace the loss with the instantaneous loss. Now, if you take derivatives from this thing and actually do the, you know, set it equal to 0, this is what the recursion looks like. So in stochastic mirror descent, what happens is rather than update the estimate of the weight vector along the negative direction of the instantaneous gradient, you update the gradient of the potential evaluated at your estimate. Okay, so this is what the update is. And so the reason why this is called mirror descent is because the way originally this was interpreted was that, you know, you take your W and you map it to the space of the gradient. So that was considered like a mirror space, and you do the update in the mirror space. Now, of course, this reduces to SGD when the potential is just half the square, because the gradient of this is just W, and so this becomes Wi equal to Wi minus 1 minus eta times the instantaneous gradient. So it's a generalization of SGD, but it's more general because you can put any strictly convex potential. And again, the reason why we need strict convexity is because when the potential is strictly convex, this gradient function is invertible. And so from this equation, you can invert this gradient function and explicitly find Wi if you need. So that's what stochastic mirror descent is. And again, it will not converge similar to SGD unless there is a W that simultaneously makes all these gradients 0, the instantaneous gradients. In other words, if there's a W that interpolates the data, which is the regime we're focused on anyway. So what is this SMD good for? Again, I'm going to look at the linear case. I'm going to look at an arbitrary, say, loss function now, not necessarily quadratic. And so this is what SMD will look like for this loss function. And so it turns out that there is a counterpart to the theorem that I showed you earlier. And, you know, back in the 90s, I wish I knew about Bregman divergence, because back then I was always trying to extend the result I showed you on H infinity, and I was never able to. This is the right way to do it, through Bregman divergence. And so what this says is that if my step size, again, is small enough, so that this quantity is convex for all I, this is convex, L is convex, well, L may not be convex. But since this is convex, if eta is small enough, this difference will be convex. Then it turns out this min-max, where the difference with what we had earlier is we're measuring the uncertainties in terms of Bregman divergence. For V, we're measuring it in terms of the loss, and upstairs again, this is Bregman divergence, and this is the Bregman divergence of the loss. You do a min-max, the solution is SMD. And so that's a remarkable thing, I think. And, you know, so it again, it specializes to SGD when psi is quadratic and so on. Maybe I'll try to quickly, I don't know how I'm doing on time, maybe just give a sense of the proof. So the proof is very similar to what, you know, we did in the SGD case. You just have to define quantities that are counterparts of the innovations and the prediction errors. So there's this quantity which I will define, which is the Bregman divergence of psi minus eta L. This I assumed is convex, so the step size is small enough, plus eta Li. So this EI is something non-negative, because both terms are. And then, you know, you can show that there's a conservation law, a local conservation law, there's a global conservation law, And because this term here was positive, you can drop that off, you get a lower bound, and the ratio is what we had. Okay, so it's very similar in spirit. And again, the reason why we could extend the result here is because this Bregman divergence behaves very much like quadratic. So pretty much everything we did for SGD is extendable once you understand it. And so the question is, what is this good for? Okay. And so I'm going to, again, maybe look at this over-parametrized case. So recall we have more parameters than data points. There's a whole space that interpolates the data. And so when we interpolate the data, there is no noise. And so in this, if you will, global conservation law, this term is not there because there's no V. And so this is what you get. Now, all the terms here are non-negative, and so again, you can show the same thing. So first of all, you can show convergence. So this is fixed, and so as m goes to infinity, these two terms have to remain bounded. And so what this means is that each of them has to be bounded because they're non-negative, and so this means that, you know, so for example, if you look at these second terms, these two things should match. Again, I'm going very quickly, and so that implies convergence, basically, if you look at this term. Okay, so again, the proof of convergence is identical. It just uses the fact that these summations have to be finite as W goes to infinity. And then once you get convergence, it's also easy to show that you converge to something that interpolates the data, because both of these terms have to go to 0. This means convergence. This means the loss goes to 0. So W infinity, what you converge to, has to interpolate the data. Okay, so this is identical to what we saw earlier. And so the question is, what is it that we converge to? And so again, if you look at these terms, so this term here clearly doesn't depend upon W. It just depends on W naught, because it's, and the measurements, or, you know, the data, because it's from the algorithm. This term here potentially can depend on W, but it turns out that it doesn't. So when you write it out, so this is the definition of the Bregman divergence. Okay, at W's that interpolate the data, this term is 0. And this term here, when you multiply with xi transpose, this gives me yi. And so when you look at it closely, it's independent of W's that interpolate the data. And so we get exactly what we had earlier, that this Bregman divergence between W and what we initialize with is the Bregman divergence between W and what we converge to, plus terms that are independent of W's that interpolate the data. And so we get the same thing. If I minimize the left-hand side, it's equivalent to minimizing the first term on the right-hand side. This doesn't play a role. So W infinity is what minimizes this, because it's 0 when W is W infinity. And so we have this remarkable result that what we converge to when you do stochastic mirror descent is the solution that interpolates the data, but that's closest to what I initialized with, not in Euclidean distance, but in the notion of Bregman divergence. Okay, so again, we'll call this implicit regularization. Now there's an important case. So if I initialize again with 0, and if I assume the potential is minimized at 0, the Bregman divergence, so if this, I plug in 0 here, gives me the potential. And so when you initialize with 0, or with whatever it is that was minimizing your potential, then W infinity actually minimizes the potential. So you can get the minimum potential solution when you initialize with whatever initially minimized your potential. Okay, so you can do this. So previously we could find the minimum 2-norm solution, but now we can find the minimum whatever strictly convex potential that you want solution. So this is again implicit regularization, and you know, for whatever desired regularization that you have, you can just choose the corresponding potential. Okay? And then run SMD. And so as an example, you can, you know, if you choose your potential to be negative entropy, you can find the maximum entropy solution, say. You can do whatever you want. And so, for example, for those of you who know compressed sensing, in compressed sensing, you want to interpolate the data but find the minimum L1 norm solution. And now this suggests that one algorithm to do this is to run stochastic mirror descent. Okay, you choose this as the potential. In principle, you cannot take the one norm as the potential because it's not strictly convex. But if you take a 1 plus epsilon norm for any non-negative epsilon, it is strictly convex. And you can run the algorithm, and this is a simulation, it works. So you can actually use SMD to do compressed sensing, but you can use SMD to do any regularization that you want. Okay. Again, so this is implicit, because when people conceived of SMD, this is not what they were planning to do. This is a property that the algorithm has. It's kind of implicit in the algorithm. Okay. So back to deep learning. So maybe the next 10 minutes, I want to wrap this up by saying, what does this have to do with deep learning? Okay. So in deep learning, we have a nonlinear model, which I've written here. So again, t data points, little n is the dimension of the input, capital N is the number of parameters that we have. Typically, capital N is bigger than n, way bigger. Again, we can have a loss function as before. We're going to do SGD, which is fine. And so the min-max optimality that I showed you was totally algebraic, and so holds here as well. So that's fine. So when you run SGD or SMD on a deep network, this property holds. And so let's see what the implications are for this over-parametrized setting, right? So when we have more parameters than we have data points. Okay, so in principle, what this means, and I'm hand waving here a little bit, but this can be under some assumptions, on the width of the network, this can be made rigorous enough. It means that we can interpolate the data. So there are weight vectors, because we have more dimensions in the weights than data points, that perfectly interpolates the data. So there will be some solution space that interpolates the data. In the linear case, it was a linear affine subspace. Now it's some nonlinear set, maybe it's a manifold, whatever, but and again, it has dimension capital N minus T. The codimension is T. Our fundamental identity still holds. Again, because we're interpolating the data, there's no summation over the loss functions of the V's, because there's no V. So this still holds. And so when we proved convergence and implicit regularization in the linear case, we used the fact that these two terms were we used two facts. We used the fact that this term here was non-negative, and we used the fact that this term here was independent of W. Okay, so that's what I'm saying here. We needed this to be non-negative. Sorry, it was... Yeah, right. I need this to be non-negative, and I need that always is non-negative, and for it to be independent of W's. The problem is really this term. And in the deep learning case, because we have this non-linearity, neither of these two things holds, and so that is really the difficulty. But the good news is that they hold locally. So the reason why this is not non-negative is because Li, once you have something non-linear here, is no longer a convex function of W. And so when I look at L and I subtract out the first order terms, the difference is not necessarily non-negative. Right? So if you have some function that's not convex, and I look at the tangent at some point, it can go above. But the good news is that if you're in some local neighborhood of this tangent, you're typically below. So if you're close enough to the interpolating W that minimizes this, then this is true. So locally it's true. And furthermore, you can show that when you're close enough that the dependence on W is weak. I'm hand waving. All of this can be made precise. And so this is what we can show, okay? So I'm going to define something called W star. So this is the minimum over everything that interpolates the data of the distance between such points and what I initialize with. I'll call this W star, okay? This is what we converge to in the linear case. When we initialize with W naught, we would converge to W star. I would like to say that the same thing happens in deep learning, but here's the theorem. Okay, so there's some epsilon such that if I initialize, such that if my initialization is close enough to this W star, then two things happen. First of all, mirror descent or stochastic mirror descent converges to something that interpolates the data. And secondly, it doesn't quite converge to W star, but what it converges to gets an order of magnitude closer to W star than I was originally. So this is not quite zero, but it's little o of epsilon. Whereas originally, this was on the order of epsilon. And, I almost, implicitly regularize because the distance between W naught and W infinity in Bregman divergence is almost the distance between W naught and W star. This was of order epsilon. This, of course, is small. So what this says is that, well, let me take that out before I say it's dissatisfying, that we kind of, if we are close enough, we approximately implicitly regularize. So we get very close to this W star. We don't get to it exactly, but we get close to it. And so you might say, okay, this is dissatisfying. What's the big deal? You're saying, okay, if I start off close enough, then I converge and I converge almost to this W star, but this is predicated on being close enough. And so
I have one question, Babak.
Yeah.
Should I worry about that all this is happening in the divergence kind of space rather than, or this is, you could also prove this with
no, this is for any potential. So I can prove this, this could, so if psi was just, 2 norms. Yeah, I can do
okay.
So actually, I'm going to show you, there's an advantage of looking at this. I'll show you, I hope I'll have time to do that, to show you that there's an advantage in doing this generally, okay. Looking at it generally. But yeah, the theorem holds in the Euclidean case. So when you're doing SGD, these things hold where, this is just the squared Euclidean distance of the difference. So if you're close enough in Euclidean distance, you converge to something that's much closer in Euclidean distance and that approximately, minimizes this thing because the difference is little o of epsilon. Now, what I want to argue is that in the highly over-parametrized case, which is what happens in deep learning, where you have, orders of magnitude more parameters than data points, that this setting, I want to argue, happens by fiat. It kind of naturally happens. And I don't know if I want to give you the argument, because here I'm actually, I will skip the math because it's a little bit hand-wavy. But what I want to say is that it turns out that when you're in, if what you can show is basically the following thing. So if I start off with a W naught, and this W star is, what I said it would be. So it's, where is W star? And I'm doing this for the 2 norm case, for example, because it was easier. So W star is the solution to this. So it's something that interpolates my data and is closest to W naught. Okay. So what you can show is that W star minus W naught is on the order of T to N, where T is the number of data points, N is the number of parameters in your model, okay? And so really what this is saying is that if I am, say, in a space of dimension 1 million, and I have 1,000 data points, okay? The space that interpolates the data will be 999,000 dimensional. It's very high dimensional. And so pretty much any point W naught you choose, its distance to this interpolating manifold, because this is the distance in the interpolating manifold, W star is the closest point on the manifold, is very close. It's on the order of 1,000 to 1,000,000. Because think of being in a million-dimensional space, you have this underlying, subset which is very high dimensional, and any point you take will be close to it, and you can kind of characterize this. And so I think the reason why these deep networks have worked so well is because basically of this. So when you go extremely highly dimensional, everything becomes local. Any point you choose is close to the interpolating space, and so this theorem applies. So this you get by fiat, because this is like order of t over n. So it's like 1,000 over 1,000,000. And so once you're close enough, you will get convergence, which is what people observe. Every time they run SGD on these, deep networks, they end up interpolating the data. And furthermore, that you kind of get this implicit regularization. So basically, this is what I'm trying to say, that when you're in this very highly over-parametrized regime, any random initial condition is close to this manifold. So in other words, W naught is close to W star in Bregman divergence. Once you're close enough, you get convergence. And what you converge to is very close to W star. And so what this says is that in the highly over-parametrized case, if you run SMD or SGD or any of these, you converge to a point that exhibits implicit regularization, right? So if you run SGD from an initialization in deep learning, you converge to something that's very close to the minimum 2-norm solution on the weights, okay? And so what I want to argue is that the reason why deep networks generalize well is because they find very special solutions. They're not finding any old point that interpolates the data. In the case of SGD, they're finding the minimum 2-norm weight that does this. And perhaps that's the reason for the good generalization. And so this concept, people are now calling the blessing of dimensionality, as opposed to the curse of dimensionality. So when you go to very high dimensions, you get convergence and interpolating the data for free. But the remarkable thing is, because of the use of the algorithms that we have, the solutions that we get are not any old solutions. They are actually, solutions that generalize well. And so let me go back to this more colorful presentation to show you some simulation results and maybe convince you of what I was trying to say. So this was a less mathematical version of the presentation I gave you, but I guess this was the Shannon lecture. So, okay, so here is a picture that I want to focus on. Again, I think this kind of describes the difference between traditional, neural networks in the 80s and 90s and neural networks today. So in the 80s and 90s, when people were so focused on don't overfit the data, don't overfit the data, so you were looking for like a global minima that you're trying to solve because, so you have fewer parameters than, say, your data point. And so when that happens, typically you get lots of local minima, and every time you'd run SGD or gradient descent or whatever, you'd get into a local minima. And so the question was, could you find the global minima? And so this is like finding a needle in a haystack. Where on earth is this global minima? Once you go to this highly over-parametrized regime, there's uncountably, infinitely many weight vectors that interpolate the data. In fact, it's super high dimensional. As I said, it's 999,000 dimensional in a million-dimensional space. So the picture is really down here. You have needles galore. There's so many things that interpolate the data. The question is, can you find a good needle? Can you find a solution that interpolates the data, but that generalizes well, okay? And so that's where regularization can help you. If you find a solution that has some regularization property, maybe that's why it generalizes well. So the point really is that these stochastic gradient descent or mirror descent, they find special needles. And as I said, the needles that they find are ones that kind of approximately solve this problem. they find, and in particular, if you initialize appropriately, they will find the minimum potential solutions. Okay. Okay. So this I put out there for the skeptics in you, because you've listened to all of this and you might say, okay, is this true or not? And so we did some experiments. And so we did it on 2 data sets on MNIST, and something called the CFAR10 data set. So the CFAR10 data set is a data set of, I guess, images. There's 10 different types of images: ship, dog, deer, bird, cat, so on. So we took this data set and we took a standard deep network architecture, which is called ResNet 18. 18 because it has 18 layers, and because we could then compare to what other people had done. And so we did 2 types of experiments. So we wanted to verify, first of all, that the theorem is true, that we converge to, the closest point, in whatever Bregman divergence we chose. And so we did extensive simulations, and I'll talk about this in a second. But just a few words about the CFAR10 data set. So it's 60,000 images. We use 50,000 for the training data, and then 10,000 to evaluate the generalization error. So think of this as being 50,000 data points. And then ResNet 18 has 11 million weights. So that already tells you something. So there's, there's more than 200 times more weights than there are training points. So this is highly over-parametrized. And so we did extensive simulations. We generated, lots of solutions that, interpolated the data. And in every case, what a particular SMD, whether we used L1, L2, L3, or L10, these were the different potentials that we used. Whichever one we used, what we would converge to was always the closest in the corresponding Bregman divergence to what we initialized with compared to all the other interpolating solutions that we had. So that was some kind of thing that supported the theory. Now, the other thing I want to show is that, choosing different potentials actually makes a difference, okay? So what I'm showing you here is the distribution of the weights after training that you get from ResNet 18 on the CFAR10 data sets. So this first one here is when you minimize an L1 norm. This is the L2 norm, so this is SGD. This is when you take the potential to be the L3 norm, and here's the L10 norm. And you see the way, so after training, we get things that interpolate the data. So, I can't show you 11 million weights here, and so I'm showing you the distribution of the weights, okay? And I'm showing you like the distribution of the absolute value of the weights. So the actual distributions go to the left as well. And so the thing I want to emphasize is that all 4 of these perfectly interpolate the data. So on the 50,000 images that we used in CFAR10, they identified cats as cats, dogs as dogs, and so on. Okay, but certainly these are different weight vectors, and all of these were initialized with the same point. So we initialized at a point very close to 0, and ran L1 SMD, SGD here, L3 SMD, L10 SMD. And so the fact that the weights are different is just an artifact of the algorithm, because we initialized with the same thing. It was the same data set, and we interpolated. And if you look at these, they actually kind of say something. So SGD, remarkably, has a distribution of weights that looks Gaussian. And there's a lot of recent results, there's something called the neural tangent kernel and so on, that kind of argue that if you do SGD, or gradient descent, that the weights should behave Gaussian, and they do. This is the L1. So the L1, if you think of it, encourages sparsity. So this is finding a weight vector that interpolates the data, but has the smallest L1 norm. So it should be more sparse. And if you look at it, it has a lot more mass at the origin than, say, this guy does. So maybe there's twice as many zeros in this solution than there is, say, for SGD. And so this kind of jives with the fact that, our regularizer is encouraging sparsity. So with L3 and with L10, the distribution of the weights moves to the right, which again makes sense. So for example, L10 we used as a surrogate for L infinity. So this would like to limit the peak value, if you will, of the weight. So this is a weight vector that interpolates the data, but kind of, you know, minimizes the peak. And so the distribution clearly has moved to the right, okay? So this is already showing something. But the most remarkable thing, which I'll show you next, is you might ask, okay, so these are 4 different weight vectors. Each has a different regularization. They all interpolate the data. They clearly look differently. But do they generalize any differently? And which one generalizes best? So when we did these experiments, we'd heard everything about sparsity and compressed sensing and so on. Our expectation was that this guy here should generalize best because it has the fewest number of actual weights. It had lots more zeros than these other guys. And so that's a question, do these generalize differently? And so here is the results of simulation. So this is the accuracy on the test set. So the higher the number is, the better. This is the L1 norm, this is SGD, this is the 3 norm, this is a 10 norm. Each of these is 8 points because we did 8 different runs of this. And so the remarkable thing is that the L1 is the worst. It has the worst generalization error. SGD and this guy have the best. They're around 93%, comparable performance. And in fact, this is on prior to our work on CFAR 10, ResNet 18, 93% was the best performance that we could get. And so the thing that really baffled us and blew us away was that this L10 regularization, the guy I show you here, consistently had the best performance. And this broke the record of the performance of CFAR 10 on this ResNet 18 architecture. It's more than, I mean, it's a good, even more than 1%, I would say, better than this. It's like a 1.5% better. And so this really shows that this choosing the right regularizer, using different regularizers helps, okay? Now, I have no clue why this is performing better than that. No clue whatsoever. Again, it's very counterintuitive. I would have thought the L1 would have been best. It's the worst.
You suspect it's specific to the data, or
I don't know. So that I will end with that slide. So basically, yes. So I don't know whether it's specific to the data. I don't know whether it is specific to the CFAR, to the ResNet 18 architecture. I suspect it might be. It has to be related to the data. What else could it depend on? I don't expect this behavior to hold for every data set. I don't know. But this just shows you that there is a difference in choosing different regularizers. It's not just that the distribution of the weights look different, the performance looks different, and consistently so. And so I'll conclude now. I know I've gone way over time. So there's a few things that I want to emphasize. So first is this blessing of dimensionality, okay? So when you go to these very high, dimensions, you get all these kind of interpolating solutions. There's so many of them. Everything becomes local. Every point you choose is kind of close to the interpolating set. So these interpolating solutions, these zero-loss solutions, are easy to find. And so the question really is, what interpolating solution is it that I converge to? So that is algorithm dependent. And, I think in this setting, it was really happen chance, and it was luck that people were using these SGD type algorithms which had implicit regularization in them. In other words, they give you the minimum 2 norm solution or something very close to it. And I would argue that that's why they generalize well. We're not going to some arbitrary W that's interpolating the data. We're finding a very special one. As I said, so SGD finds the minimum 2 norm weight vector. Another thing about this is the loss function really didn't play a role in any of the analysis or any of the results. So the loss function doesn't matter a whole lot. What matters is the potential, whether it's L2, which gives SGD, or anything else, okay? And again, this is all happen chance because none of this was intended. This was, post-analysis. But the burning questions are, why was L1 worse? Why was L10 the best? Was this, again, data dependent? Was this architecture dependent, and so on? More importantly, what is a good regularizer, right? If I have a data set, is there some way I can infer what the good regularizer is to use? And finally, I think what's really missing, and as information theorists, I think, we can probably contribute here. What is the right generalization theory for deep learning? So, in conventional learning, people had things like VC dimension and so on. Those give you vacuous bounds here, because in this deep learning setting, you interpolate the data. So you cannot really give a universal generalization error bound for all weight vectors that interpolate the data, which is what VC dimension does. Because some of the weight vectors that, interpolate the data have better and worse generalization errors. There might be some that don't regularize anything that could have horrible generalization errors. And the VC dimension bounds all of them. So the bounds are very bad. And so what you really need is some kind of algorithm dependent bound, or, regularizer dependent bound that says that, if you're performing some learning task, and this is the size of the data set, and this is the architecture, and this is the algorithm you're using, that this is a bound on the generalization. So I think there's lots of burning questions. And so I kind of hope that in this talk, I exposed some of the elephant, basically trying to say that the algorithms matter, that there's a lot more going on in the algorithms that comes to the eye. That at first you'd say, oh, this is just gradient descent. What's exciting about there? They have these implicit regularization properties built into them. And I think it raises a lot of interesting questions, because we now have some idea of how to design regularizers through this potential function. And so questions are really, what is the right regularizer? How does it depend on the data set or the network architecture that you're using? And can you develop a generalization theory for this? So I know I've gone over time, but I thank you for your attention. If there's time for questions, I'd be happy.
Thanks a lot, Babak. So maybe we can take one question from the audience. I asked many questions, so I don't know if there is a question in the audience. We can take one.
Hello, Babak.
Yes.
Anusha is here. You guys hear me? All right, good.
Yeah.
So thanks very much for your talk. I have a very quick question. So if you take this potential to be like LP norm, okay?
Yes.
In general. And so I was wondering how the vanishing basically rate of that little o of epsilon that you have is going to be in terms of that P. I mean, the norm that you take.
That is a very good question. So I don't know if I have it. You're talking about this thing here.
Yes.
Yeah. So work to be done. So the analysis we did here was kind of very sloppy. I wouldn't say very sloppy, but we did not keep track of the coefficients.
I see.
So I don't have an answer to that. So we did this not for an LP norm. We did it for a general potential. And so I'm trying to think in terms of how it depends on the potential. So it certainly depends. So this little o of epsilon certainly depends on the network architecture. It depends through the Jacobian, if you will, of the, so if you look at the F function that I have, which is how inputs in this deep network are mapped to the output, there's a Jacobian associated with that. So that Jacobian plays a big role.
I see.
But I'm trying to think the potential. Yeah, I would think again, so the what would matter there is I would think again like the Hessian of the potential, because so the way these results are obtained is you kind of linearize everything in sight. So you keep things up to quadratic. So linearization really means that when you look at these functions, potentials, and so on, you do a quadratic expansion. And so what shows up, as I said, is the Jacobian of the network, and I think the Hessian of the potential. But I'd have to look at it closer. But there is a dependence on P, absolutely. So that the coefficient in front of this depends on that. So for example, I know more because I've looked at it more in terms of the architecture of the network rather than the potential. So the width of the network matters a lot. So the wider your network is, the better. And so I will say one other thing. So deep networks is about as big a misnomer as exists. These things should really be called wide networks, right? If you ever drew a picture of them. So ResNet 18, as I said, it has 18 layers. So you might say, oh, that's a lot of layers. But there's 11 million weights.
Yeah.
So you can kind of imagine how wide these have to be to accommodate 11 million weights. And so that wideness matters a lot. But I don't have anything more intelligent to say about how P plays a role here.
Thank you.
Okay, thanks again, Babak, for the great talk, and thanks everyone, and we'll see you next Friday then.
Thank you, Salim. Thank you all. Yeah, take care. Thank you.
Bye-bye.